Okay, welcome everybody to the last colloquium of the semester. Today we're very pleased to welcome Professor Brad Marston from Brown University to give this talk. So Brad is a well-known condensed matter physicist. He's the director of the Brown Theoretical Physics Center. He's a graduate of Caltech, and he received his PhD from Princeton University. And subsequently did postdoctoral work at Cornell as an IBM fellow. He's been a visiting professor at a number of institutions, including MIT, Caltech, École Normale Supérieure in Lyon, and a general member of the Kavli Institute for Theoretical Physics, KITP, in Santa Barbara. Professor Marston was an Alfred P. Sloan Fellow and was a recipient of the National Young Investigator Award. In 2008, he was designated an NSF American Competitiveness and Innovation Fellow and an APS Outstanding Referee. Marston is a fellow of the APS and has been on the advisory board of KITP and a counselor for the APS Division of Condensed Matter Physics. I said he is a condensed matter physicist by training, but in recent years, he has expanded his interest towards geophysical fluid dynamics and plasma physics. And in particular, he's leveraging some ideas that have been prevalent in condensed matter physics to shed light on different types of dynamical behavior in the Earth's atmosphere. For our purposes here, I think it's very important to mention that he is the president-elect of the APS, and he will take over on January 1st as the president-elect of the American Physical Society. On a personal note, I would like to say that he's a great hiker, and he's one of the few people who has almost completed the Pacific Crest Trail. Is that correct?
Well, there's quite a few people who've completed it, but
that I know.
Okay.
That I know. So let's welcome today Professor Brad Marston, and he will tell us about waves of topological origin in the fluid Earth system and beyond. Welcome, Brad.
Thanks very much, Hector. It's a pleasure to visit here and meet with old friends and colleagues and meet some new ones. So as Edgar mentioned, I want to tell you about this connection that we've made between ideas of topology that have been used in condensed matter physics especially to the fluid Earth system and beyond. You'll see what I mean, I hope. So this is work that involves a number of collaborators, of which only some of them are listed here. But I wanted to highlight especially Zoe Zhu, who has been working very hard with me on a plasma experiment, which I'll tell you about. And she's about to become a faculty member at Boston College. So the outline of the talk is I wanted to review briefly the application of topology in quantum matter, and then discuss how it can apply to some classical systems that have a lattice structure. And then I'd like to point out that the lattice is not essential and that these ideas can be brought over to continuous problems. I would like to also emphasize in the systems that we're going to be looking at the role of broken discrete symmetries. Then we'll turn to the mathematical heart of the talk, which is the shallow water equations, which are the simplest system of equations that support these types of waves in a rotating coordinate system. That's going to have relevance to the largest climate oscillation on the Earth on human timescales, the El Niño Southern Oscillation. And we'll diagnose some topology directly from observations of the stratosphere. And I don't know if I'm going to have time to talk about some of these other topics, except for I'd like to show you something of our work with plasmas. So the entry of topological ideas, the mathematics of topology into condensed matter physics really came through the integer quantum Hall effect, or that's at least one of the entry points. And so this is one of the early quantum Hall devices. It's a semiconductor system that's in a magnetic field, and it was observed to great surprise that the Hall resistivity as a function of magnetic field did not have a straight line form, but had these plateaus at very precise values of the Hall resistance. And so this is early work by von Klitzing in this discovery, and a kind of operational way of understanding perhaps how this might come about is that in the presence of a strong magnetic field coming out of the plane here, that electrons execute cyclotron orbits in this magnetic field semi-classically, but along the edges of the system, they aren't able to complete their orbit, and so there is a sense of motion in one direction, a unidirectional motion, that the current is flowing in, and therefore if there's dirt or impurities such as visible in this photograph, then backscattering is inhibited by this unidirectional motion. So that's a kind of mechanistic way of understanding things, and it is correct insofar as it goes, but a deeper understanding was provided through the work of a number of people, but especially David Thales, who calculated the conductivity of this system using linear response theory, using Kupo formula, arrived at this expression, and realized that the valuation of these integrals gave an integer. Now, he didn't realize it at the time, but the thing that he was calculating is something called the Chern number, which is a topological invariant. And so the fact that it takes on these integer values could give an explanation for the quantization of the Hall conductance, which is so precisely quantized that it's now serving as the international standard for resistance. Now, I'm not going to go through this calculation, but I want to illustrate basically the same ideas in the context of other systems, classical systems. And the key point is that topology, as I mentioned, is a kind of qualitative measure of something. It's a qualitative measure of the shape of objects. They might not be objects in physical space, but on different types of manifolds. There's a common example, of course, is this one where we would say that a donut is the same topology as a coffee mug because they both have a single hole. And if you wanted to get rid of that hole in the handle or in the donut, you would have to cut the material, do something violent to it, discontinuous. Similarly, a Mobius strip, if we wanted to straighten it out and make it an orientable surface, we'd have to cut that paper and twist it, untwist it, and glue it back together. Another application of topology is the so-called hedgehog theorem or hairy ball theorem. If we had a ball that's covered with hair, we wanted to comb that hair flat everywhere, then we would find that that's impossible to do. There'd always be some bald spot or a hair that's pointing up on a sphere. But if we tried to do that on a torus, we would be able to accomplish that. All of the hairs could lie flat. And so the origin of this work happened during a sabbatical I spent in southern France, in Lyon. And in France, they have these hedgehogs, which aren't present in North America. And we unearthed one in our backyard while raking the leaves, had to figure out how to place it back into its habitat. It was sort of hibernating. And so, it's a pretty good approximation to a hairy ball. And I'd like to think that this was some sort of signal to pay more attention to topology. So Richard Feynman, in his lectures on physics, in particular the chapter on fluid mechanics, said, the next great era of awakening of human intellect may well produce a method of understanding the qualitative content of equations. Today we cannot. Today, we cannot see that the water flow equations contain such things as the Barber pole structure of turbulence that one sees between rotating cylinders, rotating co-ed flow. Today, we cannot see whether Schrodinger's equation contains frogs, musical composers, or morality, or whether it does not. Well, so what I'd like to offer today is the idea that topology can be used to get some qualitative information in certain situations, and it turns some complicated problems into simpler ones. So a progression in condensed matter physics in the application of topology came with topological insulators, which are similar in some sense to the quantum Hall effect, except they don't break time reversal symmetry. There's not a preferred direction for a current. There's current flowing in both directions on the edges, different directions for different spins, roughly speaking. And so, but you can think of this in some sense as a doubling of the quantum Hall effect. And the nice thing about this is that the energetics are sufficiently high that spectroscopy can be done to look at the band structure of these edge modes using angle resolved photoemission. And we find something just like this, where we have counterpropagating modes at the edges according to the predictions, in agreement with the predictions of this topological insulator theory. We're going to see something very similar to this in the case of atmospheres that was actually discovered before topological insulators. Now, it's really the wave-like aspect of the Schrodinger equation which makes its entry into the topology. And therefore, other wave equations can have topological physics. And here's a bunch of classical examples. This one we're going to look at in a little bit more detail. It involves a bunch of gyroscopes all spinning the same direction. They're coupled together by magnets so that waves can propagate. But there's optical systems and acoustic systems that have similar properties. These are all basically classical systems, and yet these notions of topology apply to them. So let's look at this example that comes from William Irvine's lab at the University of Chicago. What we're seeing, we're looking up at a bunch of small gyroscopes that are hanging suspended from the ceiling, and they have magnets on them so they're able to jiggle each other. And they're all spinning in the same direction. And what is going to happen is one of them is going to be set into motion, and that is going to be highlighted by this color. And what you see is this edge mode propagating around this system. It doesn't penetrate into the interior. If those gyroscopes hadn't been spinning, that energy would have spread out through the interior of this system. But because of this topological nature that I will explain in a moment, the energy is confined to the edge of the system. So what we did is ask, can these ideas apply to a continuous system that isn't on a lattice? So a continuous fluid system, for instance, like the Earth's atmosphere or oceans. And so why would we want to do this? Well, the Earth is rotating, and so it breaks time reversal symmetry in a sense similar to the application of an external magnetic field in the integer quantum Hall effect. So if we think of a rotating planet here with a angular rotation rate, a vector pointing up from the right-hand rule, and we look at it in a mirror, then the mirror planet is rotating in the opposite sense. But if we then follow that mirror operation with time reversal, if we play the movie backwards, then we restore the sense in which the planet is rotating. And so this is a manifestation of a theorem called the CBT theorem. Here we only have parity or mirror reflection and time reversal, and the product of P and T leaves this system unchanged. We can view this algebraically in terms of the formula that relates the acceleration in a rotating frame to the acceleration F over m in an inertial frame from Newton's law, which has these two extra terms, the Coriolis term and the centripetal acceleration. And we notice the acceleration involves two time derivatives of position with respect derivative position with respect to time, and velocity is just 1. So if we reverse the sign of time, then we also have to reverse the sense of omega in order for this equation to have the same form. Now, on the Earth, most of the fluid motion is in the horizontal direction. So the component that we're interested in this cross product in the Coriolis term is the local vertical component of the angular rate of rotation. So here in Berkeley, or we look up vertically, we need to find the dot product between this local vertical direction and the North Pole. And so that gives the Coriolis parameter, which is 2 times the rate of rotation of the Earth times the cosine of the co-latitude. So it is a quantity that vanishes at theta equals 0 as we go through the equator. It changes sign from positive in the northern hemisphere to the negative in the southern hemisphere. And therefore, the equator is the boundary between 2 hemispheres that break time reversal symmetry in opposite senses. And it's at the interface where we know that these topological waves can be found. So this is what piqued our interest in the fluid Earth system. So a number of objections were raised when I discussed this idea with people who were experts in thinking about topology in condensed matter contexts. One was, well, perhaps the fluid system is too simple. It's just a fluid after all. As we'll see, that objection doesn't hold because when we look at a system of equations like the shallow water equations, we have 3 components, which is sufficient. A more profound objection is there's no lattice. There's no, we have a liquid, there's no underlying cutoff, so there's no compact Brillouin zone technically, and that's what's needed to compute a Chern number. So how are we going to calculate a Chern number? And finally, the question arises whether this important idea of bulk interface correspondence, which I've hinted at, it basically says that when you have an interface between 2 regions that have different topologies, we expect a wave to be found, whether that holds in a fluid system. And we showed that it does for linear fluid systems, but it's still not well understood what happens when we think about nonlinearity. So that's an interesting question to be explored. Now, when we look at the fluid atmosphere system, we notice that there's a big difference between the low latitudes and the high latitudes. At the high latitudes, we have these long wavelength waves called Rossby waves. At the low latitudes, there's a lot of convection. And I had shied away from thinking about low latitudes because of the complexity of this, all of this going on, and had turned my attention mainly to high latitudes and thinking about applying various statistical theories to the fluid. But it's going to turn out that it's actually the low latitudes where this topological physics is important because, again, that's where this interface occurs between the 2 hemispheres that break time reversal symmetry in an opposite sense. Now, a number of years ago, we were doing a search for a condensed matter theorist, and I was on the search committee. And when they came into my office, I handed them this classic textbook from geophysical fluid dynamics. And they were wondering why was I showing them this. It was bookmarked to a page, which when they opened it up, they immediately understood that there were waves of topological origin in this fluid system because they'd been seeing diagrams much like this over and over again in condensed matter seminars. But because physics has become siloed into these different areas of geophysical fluid dynamics, condensed matter physics, and so on, there hasn't been this communication happening across fields, which if I had picked up this book 10 years earlier, I would have been able to maybe make this connection, but I hadn't done that.
Quick question.
Yep.
Who wrote the book?
This is, let's see, I forget who this is. This is, I can't read it right now, but yeah, I can get it to you. So my French collaborators, this is a particular type of topological wave called a coastal Kelvin wave. And it is technically a little bit more complicated than the equatorial waves I'll discuss. But you can look at this paper by my French colleagues who've worked out the application of our topological ideas to it. Here's actually an experimental demonstration of this. Here's a wave tank. We're looking down on the wave tank. There's a wave generator. This tank isn't rotating, and you can see the waves penetrate throughout the interior. Over here, this tank is rotating, and the camera is rotating with it. So we don't see it rotating. We're in that rotating frame. And you can see that now we have this unidirectional wave moving along the edge of this tank. So that's this coastal Kelvin wave. And here is the 1879 paper by William Thomson, Lord Kelvin, which is where he works out the linear theory of these waves and writes down the first wave of topological origin along the edge of a system, this coastal Kelvin wave, without perceiving the topological physics behind it, but simply by directly solving the equations of motion. So here's the wave function, and you can see it's exponentially localized in this y direction and has a linear dispersion relation. So I believe this is the first place where the physics of topology, in this sense, makes its appearance. So let's now start digging into the mathematics a little bit more. And to do that, I want to appeal to a very simple model called the two-layer model, which I have a denser fluid underneath a lighter fluid. So it's what we call stably stratified. If we have a bulge in this fluid, then gravity wants to force that bulge down. So this is like the situation of a pond, and we have this heavy fluid, water, underneath a light fluid atmosphere. If we drop a rock into that pond, we all know that waves propagate out. But if we do that on a spherical pond, the waves go to the antipode and pass through each other, and then they just go back and forth across the sphere. And so this is a view of those same waves on cylindrical projection. Now, this is a non-rotating planet. So there's a restoring force in the vertical, the force of buoyancy, gravity. But now let me turn on rotation. So now there will be two restoring forces. There's the force of gravity still, but there's also a horizontal force, the Coriolis force. And we'll start with exactly the same initial condition. Now we just have this additional Coriolis force. We drop our rock on the equator, and we have this localized non-dispersive pulse. That's the equatorial Kelvin wave. There's another wave called the Yanai wave that's anti-symmetric with respect to the equator. But in both cases, these waves are exponentially localized to the equator. We can say that the equator is functioning like a waveguide for these waves. And we need to provide an explanation for the existence of these two waves rooted in topology. So those simulations were done using an app that I've developed for the Mac. It's called GCM. It's free. You're welcome to download it from the App Store. Nature has provided us a physical example of this experiment with the explosion of the Honga Tonga volcano a couple years ago in the middle of the Pacific. This eruption sent out a pressure wave. You could just see it briefly there, that went around the Earth multiple times. It was recorded in barometers as it propagated around at the speed of sound. Since that was a pressure wave, a compressional wave, it wasn't subject to the same Coriolis forces as the types of waves that I was showing, which were gravity waves, buoyancy waves, and therefore we didn't see the localization to the equator. Now, let's look at some observations. This is a measurement of sea surface height made by a NASA satellite from radar bouncing off of the ocean, and it's been filtered to remove high frequency waves, tidal motion, so that we're only looking at longer wave periods. And the amplitude for the the anomaly in the sea surface height is about plus or minus 20 centimeters. Red means that the ocean is a little bit higher than average, and it's colored red because that's also associated with warmer water. Water, when it warms, expands, and so there's a bulge in the fluid here, and we have colder water over here. And when there's warm water off of the coast of South America, we have the El Nino. Right now, we're in the phase where there's relatively cooler water here, and we're coming out of a La Nina phase. So high pressure zones rotate in opposite directions around the equator. That's a manifestation of this reversal of time, the breaking of time reversal at the equator. If we set this into motion, we see this equatorial Kelvin wave propagating over the period of a couple months across the ocean. This is a three-dimensional view, a cross-section, now with measurements from instrumented buoys that go down and pop up to the surface, measuring temperature and other variables as a function of time. So we can see some three-dimensional structure to this, which has a lot of interesting information in it. So let's try to capture this physics with some equations. And to do that, we're going to use the shallow water equations. So here's a bulge of water viewed in cross-section. Then we have the two horizontal directions and then the vertical direction. And the equations of motion are basically expressions of conservation laws. The first equation up here is the conservation of mass. It simply says that as this bulge is pushed down, there will be a divergence. So as the bulge pushes out, as we push it down, the fluid will flow out, and so there'll be a divergence, and that's compensated by a change in the height of the fluid. So the fluid's incompressible. So that's just the conservation of mass. And the second equation is simply F equals ma. It says the time derivative of the velocity, u is the two components of the velocity in the horizontal direction, has a component, a forcing due to gravity, the buoyancy force, and then here's the Coriolis term. Then there's this nonlinear term that is due to the fact that we really need to think about a parcel of fluid. We need to be in this material derivative. We have to look at the forces on a parcel of fluid as it moves. But we're going to be linearizing in any case. So we're going to drop this term. We'll assume that u is small. So this term is dominant to this one. And we're also going to replace little h, the height, with the mean height, assuming that the amplitude of the fluctuations are small. So now we have a linear set of equations, and we can ask what are the normal modes of these equations. And if we work with periodic boundary conditions, we can convert the spatial derivatives to wave numbers, kx and ky. And there are now three components. We have the height and the two components of the velocity in the x and y directions. So we have a 3x3 matrix that we need to diagonalize. If we diagonalize it, the spectrum looks like this. We have some positive and negative frequency components and one zero frequency component. So the spectrum looks like this in wave vector space. And that will probably ring bells with those of you who think about various condensed matter systems like graphene, where we have similar types of dispersion relations. The gap between the positive blue band and the negative frequency orange band is determined by the rate of rotation, or the Coriolis parameter. And this completely flat band just represents that what we call geostrophic balance, the fact that a high pressure zone has flow circulating around it in a steady way, so it doesn't have any particular oscillation frequency. Now, if we...
With regard to the periodic boundary conditions,
yep.
Is this a period of around the Earth at the equator once?
Right now, we're just thinking about an isolated region, and we're going to put it on periodic boundary conditions just for simplicity, because we don't want to, at this point, think about the edges. So let's get rid of the edges by putting it on a torus, and then we'll consider the role of the edges. If we look at the wave function itself, we see the first hints of non-trivial topology because the phase of this wave function oscillates rapidly as we approach the origin in wave vector space. In fact, it oscillates through 2 pi, and it's that singularity in the phase that is the telltale sign that something non-trivial is happening with the topology. So that can be quantified by a winding number. So let me lay out this line in terms of the Coriolis parameter. This is positive Coriolis parameter, negative Coriolis parameter. Here's the equator. And let's just find those normal modes in the different regions. So in the South Pole, if we look at the positive frequency modes and we look at the phase of the wave function, so these little arrows are showing the argument of this complex valued wave function, we find that there's an anti-vortex here, and that's the reason I colored this upper band blue. Technically, we have to form something involving the different components of the wave function in order to make a gauge invariant quantity. So here we have the complex conjugate of the height times, say, the y component of velocity. If we do the same on the North Pole, we also have a singularity, but now it's a vortex. The phase winds around in the same sense as we're going around the equator. And therefore, that's for the positive frequency solution. So the positive frequency solution in the North Pole becomes the negative frequency solution in the South Pole if we maintain, if we want to follow the positive winding number. And that means that at the equator, there has to be a topological transition where the identity of these bands interchanges. We have this band inversion, and right at the equator, it was where f equals 0, the gap vanishes, and the 2 bands touch, and we don't have a sense of topology. So there's this topological phase transition that happens, and the winding number for any one of these bands changes by 2 as we go across the equator. The fact that it changes by 2 leads us to the prediction that there's going to be 2 topological waves at the equator, and those are the Yanai and Kelvin waves. And those are the waves, this is what the dispersion looks like when we're close to the equator. We have those bands that we saw before. Here, this was the band that was a 0 frequency, but now with a continuously varying Coriolis parameter, it becomes dispersive. But the thing I want you to pay your attention to is this Kelvin and Yanai wave. So that's the topological explanation in a nutshell for how we can understand the origin of these 2 waves. And they've been known since the 60s. Geophysicists diagonalized the wave equation in case of a varying Coriolis parameter, one that linearly varied across the equator, and found this spectrum here. So it's been not known from direct solution. It requires a little bit of work with the PDEs, but they realized that there was something unsatisfactory with this derivation. And in fact, when we submitted our paper to Science, one of the referees wrote, "The question of why the equator supports a unidirectional wave, the Kelvin wave, is interesting scientifically and important mathematically. I've asked the question myself and have been unsatisfied with my own answer as well as the answer of other geophysicists." So I think there was a sense that there was something mysterious about these 2 waves being singled out among the spectrum. Now, going back to the real Earth system, as the Kelvin wave moves across the equator, this pool of warm water also moves across the equator, and clouds are stimulated by this warm water. So the clouds tend to trace out where that pool of warm water is. And that means that satellite observations over space and time of the cloud brightness field can be Fourier transformed into wave vector and frequency space to give us a dispersion for the waves. That will be a little bit like the angle resolved photoemission spectrum that we saw in the case of condensed matter physics. And so that was done back in the early 2000s, and we see that if we look at the symmetric part of the spectrum, this is wave number versus frequency, we find the dispersion for the Kelvin waves. And if we look at the antisymmetric part of the spectrum, the waves that are antisymmetric with respect to the equator, we find the Yanai waves. This actually predates the first ARPA's measurements of these types of waves in the condensed matter context. Now, the El Nino has far-reaching effects on the Earth. As I mentioned, it's the largest climate oscillation on the timescale of years. And you know this in California because typically during a El Nino phase, there's more heavy rain in Southern California, whereas in the La Nina phase, it tends to be lighter in rain in the Southern California, more in Northern California. And perhaps the fires, for example, that Southern California just experienced in the LA basin could be associated with being in the La Nina phase. And it's actually visible in the famous Keeling curve of rising carbon dioxide. We see, first of all, the overall rise as time goes on, and then the seasonal cycle. But even if we remove the seasonal cycle, you'll notice some interesting structure there. So back when I was a graduate student, I got interested in that structure and asked, could that be associated with something? And we found that it was strongly correlated with temperature in the equatorial regions of the Earth. That is mainly due to the El Nino. The equatorial regions are warmer or cooler in some years, and that has a feedback on the amount of carbon dioxide that's added into the atmosphere, for example, by modulating fires in the Amazon basin. So this is actually looking at that sea surface height recently, and you can see that this was this La Nina phase, which is now beginning to fade. So we wanted to ask, beyond looking at the dispersion relation, can we directly get at the topology of these waves? Can we, for example, calculate from observation the winding number? And we chose, after some trial and error, to look at the stratosphere. So going up high in the atmosphere, 20 kilometers in the atmosphere. There we know that there is a very regular oscillation of the direction of winds in the equatorial region. So this is time in years from 1965 to 1990. And the colors represent whether the winds are blowing to the north or to the south. This is called the quasi-biennial oscillation because it reverses nearly every 2 years. Not exactly 2 years, interestingly, but slightly off from 2 years. And it's believed that the Kelvin waves, the equatorial Kelvin waves, play an important role in driving these oscillations. So we looked at, well, first of all, simulations of our waves, verifying that we could find these winding numbers at the for the high frequency waves, these so-called Poincaré gravity waves, and no such topology for Rossby waves, the low frequency waves, where we shouldn't find it. And then we looked at data from climate observations over a number of years at 20 kilometers height in the northern hemisphere. And so let's look at these two cases of the low frequency waves and the high frequency waves. High frequency in this context means on the order of a cycle per day. If we look at the high frequency waves, we find that indeed there is this winding number. There is a non-trivial topology in wave number space. It's a little bit hard to see probably in this figure, but the arrows are spiraling around as we go around the origin, whereas the low frequency waves have trivial topology as the shallow water theory would predict. So this was a direct confirmation that there is non-trivial topology in this region away from the equator, therefore implying the existence of these two eastward propagating waves along the equator. Edgar has been doing some numerical simulations of rapidly rotating convection and found a wave that also can propagate around the edge of this cylindrical geometry. Here he's put in an obstacle and the wave is going around this. And a former postdoc of Edgar's has done a linear analysis of these rapidly rotating convective waves and found a vortex or an anti-vortex as expected. So this is another system, somewhat different system, more nonlinear, which seems to have some of the same topological physics as the waves that I discussed. If you want to read more about the history of this, there's a nice article in Quanta magazine that came out about a year ago that discusses this and Kelvin's contributions. So we've been asking the question, can these new tools now be applied to looking at other climate oscillations for which we have poor understanding? And one of those oscillations is something called the Madden-Julian oscillation. It's a oscillation in which there is a motion of rainy weather that moves slowly across the equatorial Pacific. So it's in the same kind of location as the other equatorial waves we've been discussing, but it involves a complicated connection to clouds because the clouds are, of course, what are producing the rain. So one thing we're wondering is whether there is some topological signatures in this oscillation, which is very poorly understood. There's competing models trying to explain this oscillation, which also has worldwide effects. And we're trying to see whether those topological tools will give us any insight into this problem. On planets, equatorial Kelvin waves may have been seen in both Jupiter and I think also in on Venus. So there are other contexts where these waves can appear. We've been looking at another fluid system, a magnetized plasma. So this is in some sense returning to the quantum Hall effect, where we're using a magnetic field to break time reversal symmetry, but it's a continuous system. Again, it's a fluid system, a fluid of electrons. This is a photo taken at the Large Plasma Device at UCLA. This is Troy Carter, the previous director, and this is Zoe, and some of our the staff there that are helping us with the experiment. I'm a theorist, so they don't turn me loose in this lab unsupervised. So we have some really talented people helping us. We made a prediction for the existence of an edge mode in this, along the edge of the plasma, where the plasma fades away into a vacuum in this magnetic field. And you can see, you can now identify this chirally propagating wave at the edge. So just to give you a feeling for this experiment, that flash is the plasma, lasts in this case about 50 milliseconds. And these are probes that one can insert into the plasma to detect its density. And also what we're doing is we're transmitting microwaves at a couple gigahertz and trying to pick up those waves at different locations to see if we're seeing some chiral propagation. And here's some early results from our third round of experiments. This is showing a cross-section of the cylinder looking at the plasma. So this is high plasma density and then low plasma density. And what we found is evidence for a localization of these microwaves at the interface between the plasma and the vacuum. And this movie gives you some sense, this is on the time scale of nanoseconds, of chiral rotation. It's kind of noisy. There might be some back propagation along the outer region, but we're beginning to see some sense of these chirally propagating waves. So these waves may also play a role in the interiors of stars. We can have, in the case of a rapidly rotating star, there's a Coriolis force, and maybe in combination of magnetic field, there's been predictions of waves of topological origin at the tachocline, the region that interfaces between the interior radiative zone and the convective zone of the star. And there may be other types of topological waves in the interior of stars. So there's a new field of geophysical and astrophysical fluid dynamics that I think is being opened up by these investigations, where we use as the foundation topology, quantum physics, geophysical fluid dynamics, and try to apply those ideas to some fundamental science, planetary science, solar physics, also maybe plasmas that could be of use for fusion power. And then those may have some broad impacts, perhaps leading to better climate predictions in the future. So what new kinds of waves of topological origin are remaining to be discovered? A couple years ago, Nature magazine ran this short editorial, "Physicists, Your Planet Needs You." And the American Physical Society has responded by setting up a topical group on the physics of climate. So if you are at all interested in climate physics, and you don't need to be an expert by any means, consider joining this group. We have, that has an excellent speaker series. Isaac Held just spoke, one of the most distinguished geophysical fluid dynamicists, and you may enjoy some of the offerings. And since I'm about to become president of APS, I can't resist closing by inviting you to join the American Physical Society. Thank you.
So thank you, Brad, for a beautiful talk. So we have plenty of time for questions. Please.
So this is kind of a devil's advocate question, but it's wonderful to understand things more deeply, but have these topological techniques enable you to, say, better predict the next El Nino or something practically?
Not the next El Nino, but that wave of topological origin in the plasma was predicted by these methods. It hadn't been predicted before. And so now we're looking for it, and I think we found some evidence for its existence in actual experiments. Which I should say, like, why haven't plasma physicists looked at this? Plasma physicists also haven't been going to condensed matter seminars generally, so they haven't generally been exposed to this kind of thinking. So this is an example, I think, where a discovery can be made, and the climate system is considerably more complicated, so it's taking us longer.
So you showed the very nice dispersion diagrams, frequency versus wavevector.
Yep.
And then something happened along the wavevector axis. There was for example, the constant velocity wave converged with the parabolic wave.
Mm.
So what sets the horizontal scale on the wavevector axis?
Right. So, the gap, the frequency gap, is set by the rotation rate. And so that tells you where the curvature it becomes linearized, so to speak. So that's telling you something about the rate at which this wave, say the Yanai wave, connects from the Rossby waves to the gravity waves. That's setting the scale.
What length is it?
So the length, on the physical sphere, the length, there's a minimum wave number, but the maximum wave number could be anything because we have a continuum. So, but that frequency scale combined with the speed at which the waves are going gives you a length scale. And so that's telling you where the crossover occurs.
When you introduced the shallow water equation, you basically said let's linearize these. I think one thing that to me is often surprising when you look at all these waves is that you can make these simple linear systems, and then if you look at the effects of mean flows or nonlinearities, everything gets really messy and complicated. Yet you look at the real world observation and you're like, wow, they're still there.
Yeah.
Does this topological framework give maybe any deeper insight into why these effects and these sort of features still persist even in the presence of nonlinearities?
Yeah, I think there's a certain robustness there that persists. I wish I could give you a more quantitative answer, but until we have better tools for dealing directly with nonlinearity, then I think all I can offer is sort of empirical evidence. We've done numerical experiments with the fully nonlinear equations, starting to ramp up the amplitude of the waves. And we see the persistence of, in the case of the equatorial waves, this rightward propagation, this eastward propagation. But then we start to see additional phenomena like wave breaking. So the waves start to get very distorted. And I think this is a really interesting area for exploration, to develop better theoretical tools, but also doing some numerical experiments, maybe some real experiments with the waves to investigate the role of nonlinearity.
Maybe just a quick follow-up question. Is it some of the things you said about winding number, those were for linear systems?
Well, the winding number, the beauty of the winding number is it could be calculated for a nonlinear system from a simulation. And so effectively, that's what we're doing, for instance, with the atmosphere. I mean, it's a nonlinear, weakly nonlinear system, but we can compute it from observation. So we could do that with simulations too. So the churn number is more deeply embedded in the linear framework. On the other hand, the churn number gives us a more direct connection back to conductivity or the bulk boundary correspondence. So there's some sort of trade-off between these tools. Yeah.
Maybe just a comment, the work on rotating convection that Brad mentioned. So the edge modes there, rotate counterclockwise to the rotation of the cylinder, they persist in the presence of turbulence in the bow. So it's not just changing the topology, but you actually make the bow turbulent and the waves still around. Essentially with the same frequency. It's a mystery. We don't really know why that happens, but it's a numerical observation.
One other thing to say is that when we try to calculate the winding number lower down in the atmosphere in the troposphere, which is much more turbulent than the stratosphere, then the signal goes away. We get just this very noisy pattern, and we can't identify a well-defined winding number. So there is, if the nonlinearity becomes large enough, then this picture seems to break down.
So what are the prospects of establishing this bulk edge correspondence in nonlinear systems?
Yeah, I don't know. I think we need some new tools to think about that. So the way that it's established in the linear systems is typically by invoking ideas of geometric optics, where the Berry curvature causes some deflection of waves. I don't know how to think about that. Maybe we could do it perturbatively with weak wave turbulence ideas. So that might be an obvious first step just to warm up, but it won't really address the question of what happens when we get close to a fully turbulent state. The double period. Oh, yeah. For the quasi-biennial oscillation. Yeah, it's not synchronized with the seasonal cycle, which you might, at least to me, is surprising. So very simple models of waves driven from below. So there, these waves in the stratosphere are believed to be driven by waves propagating upward from the troposphere, can give you this kind of adjustable period. But there's some interesting things happening. So occasionally it misses a beat. So the reversal doesn't happen as expected. And there's some evidence that that is increasing in recent years. There's been a couple missing beats. Maybe it's due to climate change, maybe not. I don't think anyone really knows.
It's not off by
It seems to miss a beat. Yeah.
I'd say the classical theory, and Nez knows more than I do. Okay, but you can go back to a paper by Lindzen and Holton, who were venerable atmospheric scientists, and they're saying, look, it has to do with the Kelvin waves and these other waves moving around, but there's no direct connection with the seasonal cycle. It just happens to be
Right.
coincidence.
Yeah. Yeah.
This is the classic theory is the Lindzen, Holton. Yeah, those two guys' theory of QPO.
And you have a question there?
Maybe a naive question. So you were saying that like the ellipses on the equator, because kind of the boundary between these two counter-rotating sides. So if I go down a scale and then just think about like high or low pressure regions, they also rotate the opposite way. Right?
That's right.
So should there be edge waves between like high and low pressure regions?
Well, so those high and low pressure regions are on the background of the rotating Earth. So they're swamped by the overall rotation, right? So the circulation, the vorticity of these regions is small compared to the planetary vorticity, or technically we're in this low Rossby number limit. So I've wondered so they're up in the polar regions, there's this, in the stratosphere, there can be this reversal of the stratospheric winds. And I've looked at whether you could get to a place where the overall vorticity changes sign. And it doesn't seem to quite get there, but maybe on some other planets it does. So there might be another region to look for this.
So you mentioned that like the topologically the difference between the north and southern hemisphere, does that show up in terms of like differences in weather patterns?
Well, the sense of rotation is reversed. But other than that, well, crudely speaking, they're mirror images of each other. Of course, in the real Earth, there's a lot more land mass in the northern hemisphere and the southern hemisphere. And so there's various differences because of that are important. But sort of at the qualitative level, they're just mirror images of each other.
Okay, well, let's thank Professor Marston.
Thank you.